Hello, and welcome to Class 7 of Particle Fundamentals and Fuzzy Logic. So in this class, we're going to go over some environmental factors that are going to affect our very exacting simulations. So those kind of things might include noise and some current, maybe some forces to be relative to the current state of the shark as opposed to a very exacting goal such as rotations. And when you think about it, that's really one of the points of using the dynamics environment instead of doing all of these things in a SOP solver or code or something else like that, is that in the dynamics environment, sure, we're able to do all these things completely by ourselves, and we can get the control we need. But then we also have access to this incredible array of things that'd be very hard to do from scratch, and just the I/O and of course the integration with all of dynamics in case we would need that. So that's really important, and let's figure out how we can use this to impart a bit more realism into the simulation of the shark. So what I've gone ahead and done is we're limited back to one shark, and I set it to rigid mode because the first thing I'd like to cover is how to get the shark to move a little bit more aerodynamically, or in this case, lack of aerodynamically. So I completely am on board with the fact that the shark can swim very fast in a forward-facing direction, but I definitely don't think that this body is designed to swim sideways very well. And right now, it's reacting very evenly to the water resistance, such as this pop drag, because this little dot here doesn't really know. It's just going based on velocity. It doesn't really know that it's in water. It doesn't know that it's attached to this shark body. So let's give it some help. And so let's first integrate a little bit of side resistance. And we have to first figure out if the shark is traveling in the sideways direction or not. Here it isn't. But you see how easily it banks to the other side here, and it's still really traveling in the forward direction. And I think you'd encounter a lot of resistance because just as aerodynamic as these fins are going forward, they're equally non-aerodynamic going to the side. So let's figure out how we can impart some drag in a very specific way. Now, for this, I want to use an already existing pop node. So we can do another pop drag, which should be more than sufficient. However, we want to control this with a bit more than a simple expression in here, because this could involve some complex operations. So let's use a VOP to feed this drag an attribute to determine whether it should drag a lot or not so much. Okay, so dropping down, VOP, and I'll call this calculate side resistance. So how do we know if it's going to the side or not? So let's figure that out first. And diving in. So the absolute way that this guy is going one way or another is the velocity. So to get an angle out of that, we'd have to normalize the velocity. So let's start there. Now let's get the shark direction and the shark up vector. So I want to see how different this velocity direction is along the shark direction than the sideways direction. So in comes the direction the shark is actually pointed, the shark direction. We also want the shark up. And now let's see that exact sideways angle. So we can do that by the invisible grid that the shark direction and the shark up creates. That would be the cross product. And let's make a testing utility for that. So here I'm going to get a new parameter. We'll call this test A. All right. Let's get another test vector as well. Okay, so the red one here, that's the sideways direction. That's the direction that we want to, the closer it gets along this axis, the more we want to drag. Okay, so what are we comparing it to? Well, we're going to use the velocity, but I think the shark could probably swim upwards pretty quick and sideways pretty quick. So I want the velocity flattened about the axis here that it's turning on. So we're going to do a cross product between the velocity and the shark direction at first. Let's make sure these are normalized. Okay, so we get the sideways angle. Let's do a test B. Okay, so there's that. They're pretty much aligned right now, but you can see that there's there'll be differences here. If we're spinning this along the up vector, we want the cross product along the up vector. Okay. So there we go. And then we want to take the cross product of this orange one with the up vector. So two cross products, and we're flattening it along this axis. So between this and the up vector. And finally, okay. So here we're saying how perpendicular is this red one to this orange one here? Is test A to test B? So if it's headed pretty straight on, it's going to be almost a right angle. And if it's going either toward or away, then it'll get farther away from that right angle or closer. And if we wanted a 0 to 1 or 0 to -1 gradation from a right angle, we'd use the dot product. So let's test that out in the color. Okay, so we want the dot product between our new vector here and the absolute sideways direction, which is that. Okay. And we might be noticing that it's, we wouldn't have any drag here because it's black, but it's not always working correctly. It's only working on one of the turning angles, not in this direction where it's turning to the right. It's only working when it turns to the left. That's because the dot product it goes from 1 to -1. We want it to be centered around 0. For that, we'd finish that up with an absolute value. Okay. So now we see that as it turns, you're going to get a nice value going through here. There we go. Okay, and I think we should, now we've turned it into 0 to 1 on the left, 0 to 1 on the right. And I think we should finish that up with the ramp, so we can give it a little bit more focus. There. So really only going to apply the drag once it's pretty extreme. There we go. Cool. So now let's do something with this value we've created. So as it goes off to the side here, I want to apply progressively more drag. So that's already a node, so we don't have to remake that process along with any of the other nodes and pops. So let's get this value out of the curve. So here we go. Let's export that as shark side drag, let's say. Right. Okay, so as it gets more white, then we want to apply more of this node. So we're going to say use expressions, and we want to control this parameter, air resist. So air resist equals getting the attribute at shark side drag, and let's multiply it to make it pretty extreme to see if it's working. Finish that up. Let's see how that works. So it's not going to apply much when it's straight on, but then it should really slow down, yeah, once it's hitting that side angle there. There we go. See, so we have a lot more ability to bank those turns, as I think a real shark would. He's going to approach the target and then really spin around if he wants to go the other way. Okay. All right, so maybe not that extreme. Let's, I think I ended up, or when I was doing this at 1.5, but we definitely want a noticeable effect. There we go. A lot more realistic. Let's call this side resistance. All right, so we have that. Now let's test more of the global environmental forces. And I think we can use a simple pop force, not to be underestimated. A little bit of noise in our forces can go a long way. So for testing, we want more of a global outreach. We're not going to be able to really see what's going on one shark. So for that, let's just start with a grid and make a bunch of sharks to test on. Let's try maybe 16 sharks. Something like that. And I'm just gonna plug this into this system here. And then I'm just gonna have them facing the same direction. I don't really want their targets to be adjusting all over the place because that could be distracting. So let's just ray our grid to this target box here. Project rays, vector, and let's set the direction to the positive x-axis. There we go. So that should be the direction of our targets. Let's see how this plays out. Okay. So now they're all just going to approach the target. And to test out this force, I'm going to disable the existing velocity. So that would be on our seeking behavior. So let's just turn this off temporarily. And let's try out the force. So this is a step I like to do just because testing a force should be really, really quick and responsive. Is I'm currently just going to look at the particles without any sort of long preview. And I'm going to turn the activation just to always be constant. Okay, so we should be getting actually a lot of particles now. And let's turn off all of our other stuff. Except for the drag, which represents the global ocean current. Okay, so we're getting a lot of particles now. And let's apply this force. Let's call this global ocean current. And what's it going to do? Okay, well, not much right now, because we need some noise. So let's try amplitude of 2. All right, and noise is going everywhere. So I want to limit the scope a little bit. So let's temporarily turn down the life expectancy, maybe 2 seconds. And what I'm really interested in is I'm just really interested in the overall look here. And right now it's really powerful, and the frequency actually isn't terrible for the scale here, but I want something really, really quick and interactive that we can just play with and adjust. Okay, and it's nice to not have to cache and just to have real time. So let's turn off the roughness all the way. And now I can really clearly see the types of forces at play here. Pretty extreme on the amplitude without anything else. But it's good to at least see how the frequencies are reacting. Okay, so we have to decide, is this swirl size big or small? Or is the pulse length oscillating the way we want? So I think as far as swirl size, we can even go a little bigger, because this is an ocean. It's going to have a lot of pretty large currents at play. Okay. And then pulse length, I feel like it's moving pretty quickly. I want it to take a little longer to move. There we go. All right, so let's say I'm happy with that. Now I want to adjust the roughness. And that'd be kind of the inner turbulence present, the fractal detail. Okay, so let's say I think that's okay for the ocean current. Actually, I think it's still moving a little bit fast, so let's adjust. So let's adjust the pulse length to be still a little longer. Okay, a little longer still. It's starting to look like an ocean. Okay, so hopefully we see the value in a really, really responsive thing, because this has such, something like a simple force pop on a system like this has such a profound effect. Okay, so now I'm going to dial back the amplitude. Okay. Cool. All right, so now let's apply that to the sharks. Okay, so let's use our correct input. Okay. And that might even still be a little strong. And let's get the sharks involved again. Let's re-enable everything and see how they're affected before we activate the motion. Let's turn off the testing vectors. Okay, and here we see the effect, without any swimming behavior, we see the effect of the ocean current. And that might be really nice to add in a global set of variation for the system. We can dial down the amplitude if it still proves to be too fast. Okay, so let's plug back in the velocity. And I'm going to do another flipbook. So we can see how it's not really affecting them that much, but it definitely has a pretty profound effect. To add to the realism, there's just a little bit of variation in there now. And testing is really important with global forces. I guess you could say it is with anything, but especially when we want to work with a big picture, we really want to get the overall impression. So that's why I'm doing a lot of flipbooks here. Okay, I'm going to see a little bit of variation among our other particle logic that we've also added in. Okay. All right. So we have more of a global positional current. And now I think to add a little bit more interest, I want these up vectors to sway back and forth as well, as if there's currents from above that are kind of affecting their angles and their rotations. And the eye is really, really sensitive to rotations, even more so than I think position changes, because it's kind of like an awareness of what direction something would go in. So now let's derive a global current from an ocean surface with the particles. So I have an ocean surface here, merge ocean surface, and we can see that. There it is. And in order to get this sway back and forth as currents might be happening, I've put this into the third input. Let's take out the velocity again. And notice that when we were dealing with the tilt, we have a shark target up. And that's really cool because it means that the up vector is always going to be seeking a realignment with the target up vector. To sway the sharks back and forth, all we'd really need to do is change what the shark considers to be up. And right now this shark target up is set to export always, and it's hard-coded to 0, 1, 0. But what if we were to change that? Okay, so let's bring in the vector of the polygon that's directly above the shark. Okay, so I'm going to gather that with a bop. Okay, so how do we interact with geometry from our environment? So for that, we can have a host of things. We can do a point cloud lookup, but in this case, I'm going to do an intersect. Okay, and intersect, we're going to intersect with an external file. So we don't have any inputs here, so we have to make a parameter and gather that from somewhere else in the scene. So this is going to be a file string. Let's call this ocean. Okay, and let's gather the ocean from the third input. So that'd be up, and backticks to set this as an expression. And now we want up input path of the parent, which is particles 1. So that's quotes dot dot for dot is current, dot dot's parent. And we want input path index 2, which is the third input. Okay, so if that worked, I think it did. It's gathering the ocean surface geometry and reading that into the intersect. Now this works like a ray SOP. Okay, so now we want to ray from the current position. So that'd be the ray origin and the ray direction. Now this one is a little tricky to use, I find, because it doesn't ray all the way. It only rays as much as you tell it to. So I want the ray direction, we'll call this world up, to be going upwards. But to actually collide, I need more than a unit of 1. It stopped at 1. So the ray direction, let's maybe multiply that by a constant of whatever we think is necessary, maybe 100. Okay, and if that worked, then these guys should all go to their position. Okay, so that worked correctly. All right, so now if we play that, this is raying on every frame. Now, VOPS is a super fast way to do this. You definitely don't want to be doing this with a SOP solver and a ray SOP and stuff like that. VOPS environment's multi-threaded. Okay, so that worked. Okay, so now that we've gotten the intersect position, we've got the primitive that we've intersected with. Let's take that out of the position. So using the primitive, I'm going to get the primitive normal. So that would be primitive normal. And here's the primitive number. And the file would be also a geometry file, the same one we're using for the ocean. Okay, here's the primitive normal. And let's just preview this. Let's use a test vector to preview. And now we can see that if we preview this, we've got the polygon normals going downwards like this. All right. Cool. So I just want to negate that because these are obviously going to be going the opposite way of our up that we'd like to seek. So let's just multiply that by -1 or negate. Okay. And let's see how this plays out now. I'm just going to turn off the global ocean current. And let's flip book that. Okay, so even though they're quite sporadic, the target, the up should adapt fairly gradually because we've already got a feedback component on the up vector that's controlling the rest of our system. All right, so let's try to plug this in and see how the shark's tilt is affected. All right. So to plug that into our system, we're going to export this as shark target up. And let's view that. Okay, so this will be, let's make that red. So it's very apparent. Okay, so we've got the shark direction, the shark up, and I've got a bright red target for this up vector to go to. Let's see what happens. And we can see now that we have the up vectors trying to seek the red target vectors. Yeah, sometimes they're moving a bit chaotically, but overall, get a nice sense of current flowing through the system. If we wanted to dial that down, we might just provide a way to mix this with the existing upwards world. So in comes our ray direction, and here's our new vector. So this will be a scalar. You can call this ocean current. Now, by exporting this shark target up, that's going to feed down into the shark tilt. I'm sorry, and it'll be overriding this parameter, which is how that's working. So let's mix in about that much ocean current. Okay, and increase that a little more. And now we're really starting to see some nice subtle variation in the environment. So we've got positional variation based on a global force. We've got upwards, its sense of up and down based on the current present in the ocean. And then finally, we've got some resistance because it's in its water environment. Okay, let's do a final flipbook combining these all together. Let's re-enable the seeking behavior. I'm going to apply this randomization system instead of the ray for the targets. And let's see how this goes. And here we have it. So we've added in some global current, some positional noise, and some up vector variation to give some life into our motion. And we've added some resistance to sideways forces. So now they're able to bank and really depict the resistance of the water and of their own bodies. So in the next class, we're going to add some much needed variation. Right now, they're all swimming the same way. So we're going to go through the process of randomizing and varying our parameters to get a much more realistic, we're slowly imparting a much more realistic feel with something as basic as a point in space, a particle.